Hello again. Tonight we're going to talk about unintended meteor showers. You might be familiar with meteor showers as the debris fields coming off of comets, and they stay in the orbital path of the Earth around the sun. And the next time the Earth plows through that debris field, you get a meteor shower. So meteor showers all have an origin. Pick a comet. But now we're talking about meteor showers that nature didn't create. They were an accidental outcome of something humans did. So throughout history, there's always been unintended consequences for things that the human species has done. Sometimes it's because we had positive intentions, but we didn't realize what the side effects were, or we had positive intentions. It might have been, let's say, profit-based, and we thought we knew what the side effects might be, but it's okay. They're not going to be that bad. But then after we actually did what we did, we found out, oh, the side effects were a lot worse than we thought they were going to be. So let's ignore them and see if anybody notices or if it becomes a real problem. And then once it becomes a real problem, then we'll take some corrective action like we knew what we were doing all along. So we'll first go through a few of those things and then get into how we wound up with unintended meteor showers. Now I'm going to go through some things that seem rather harsh for the human species over time, but they're history. They're well documented. Maybe not well publicized, but you might have forgotten them being taught in history or science class, or maybe in your school they didn't teach them because it might have been embarrassing for some people. But I'm not talking about all the worst stuff. I'm just talking about some pretty bad stuff. I just refer to it as stumbling around. There was a time when gasoline engines, when you would turn them off, they would run on, or you'd be driving along and you'd feather the gas pedal and it would, as you went to come to a stoplight, as the engine RPM died down, it would not. So to correct this, we put a lead compound in the gasoline, and that made it where the explosions were slightly slower in duration, and the molecular result was slightly more cohesive, and therefore no engine run-on. There was a threshold where the engine would stop ingesting fuel and it would shut itself down, or you could throttle down and it would not. Well, we found out that that's not a great thing to be spitting out the tailpipes of cars. Everybody has to breathe, including, people that live in ivory towers. So we had to stop it. But now it's like a signage of proudness that you go to a gas pump and it says, this is used for motor fuel and contains no lead. Well, gasoline by itself doesn't normally contain lead. They used to add it, now they don't. But that's your reassurance that we've stopped adding lead. Okay, so we've often explored around the world back in the days, from the 1500s up to I guess you could say the 1900s. Went places, interacted with indigenous peoples, passed along pathogens, thank you very much, oblivious to the negative effects of, interacting socializations. Now, our society works this way, therefore your society should work that way too, political and or religious. Or we just went, hey, look, they got gold over there. Let's go over there and take it from them. That's how we used to do things. And when we found out, not only do they have natural resources, they've got a lot of people. So let's go put those people to use growing stuff or digging stuff that we want from their country. So colonizing, we've kind of, decided that's probably not a good thing to be doing. Because when you break it, you bought it, and we don't have to pay for when we broke it. So, but nowadays, the way that we do the social practice observing is using drones. We fly drones over indigenous peoples that have never been exposed to modern society, thinking that we're not affecting them because we're not touching them, we're not breathing on them, we're not getting near them, we're not putting our products into their environment. But there are groups in South America and in Africa that are, being flown over by drones. And people say, we're not affecting them. Well, if you remember back to many, many years ago in Central and South America, there were people that saw flying fish and then made little gold pendants out of it because it was something they saw. And now we're stuck thinking, well, maybe there were some more advanced humans on the planet and they were flying stuff around, and the locals made the little pins to match not flying fish, but flying aircraft. Well, if you're flying drones over a group of people that don't know what electricity is, or electronics, or drones, or radio frequencies, then you could understand how they might have their beliefs changed a little bit. Two that directly affect people is sinkholes and coal fires. So when we start taking stuff out of the ground, and it can be oil, natural gas, phosphates, it creates cavernous areas under the ground. And the area that's above the cavern may be coral, shale, and it's not that durable. And you start building heavy things on top of it, and you take out the underlying support and it collapses in. So sinkholes, when you take coal out of the ground, and then all of a sudden, lightning strikes the area where the coal mine is and pierces into the underground chamber and sets the coal on fire. The coal's got its own oxygen in the coal, so it's just going to burn until it burns out. And if these veins of coal are enormous, but too little for us to make it worthwhile our getting out, you can have what is known as coal seam fires. And up in Pennsylvania, they have got one that's been going on for a long time. You can't extinguish it. You can't put it out. And if all of a sudden there's a coal fire seam under your small town, the carbon monoxide will not be good for you. So just shut down your town, move it elsewhere. So, we do things that have side effects. If you remember, they used to test nuclear weapons above ground, and we found out that's not good, fallout kind of thing. And they said, let's test them in space, because space is way up there and it's big and shouldn't be any problems. And then they found out there's a material that comes out of those weapons called an isotope of cesium that's radioactive, and it can cause cancer in human beings. And they were doing the nuclear testing in orbit, high orbit. And turned out the cesium didn't care. It came back to Earth, and a lot of people were exposed to it. And the worldwide cancer rates bumped up because of all the cesium. So we said, probably not a good idea to be testing in space either. Then we tested underground until we found out when we started making them big enough, underground became above ground. It actually poked out the top of the dirt dome that was where the chamber was. And now you have an underground test that becomes above ground. So we banned that. And we went together with the other guys and said, I think it's a good idea to stop this. Hurts us, hurts you. Okay, good idea. So now we use computer simulations to do weapons testing, which hopefully they're accurate on the safe side, but we won't know. So some further stumbling. We'll get to the good stuff in a moment, but one more slide of the stuff. And I'm sure that there's at least one of these things will hit home to somebody like, I remember that. Sulfur dioxide in diesel fuels and the nitrous oxide combustion result of diesel vehicles, producing acid rain, affecting people's breathing, dissolving highly valued structures in Europe, killing forests in Germany. So we said, we got to stop that. Did we stop it? Actually, we didn't stop it. What we did was we came up with, well, what if we just did something to the diesel exhaust fume on its way out? We put in place different stacks on the trucks. We put in place catalytic conversion chemicals called diesel exhaust fluid, or DEF, which is an added cost. So when a diesel truck goes to fill up, fills up on diesel, and then moves over to the other pump labeled DEF, diesel exhaust fluid, and fills up a different tank with urea plus filtered water. And as the truck is going along, whenever it spews out exhaust fumes, they will spray DEF into the exhaust towers, which great. It knocks down the nitrous oxide and the sulfur dioxide. The downside is it clogs up the diesel exhausts, which means you have to take your truck in periodically and have the exhaust stacks either replaced or refurbished and then put back on. But diesel, um, we still do a lot of other diesel things like ships. You can have a ship way out in the ocean and nobody sees it out there. So no DEF fluid, no stack filters, just, okay, when it comes into shore, they change the way the engine runs so it runs more efficiently. So you don't have like diesel ships arriving and departing from Port Everglades with giant black stacks coming out. But, we mitigated some things and then others, it's way out there. No, just ignore it. Chlorofluorocarbons. Remember the CFCs and the R12 Freon? And we use those in air conditioning units, and you had to get your air conditioning unit changed out, and you had to get a different kind of refrigerator when you bought a new one because it weakened the ozone layer. The particular chlorofluorocarbons in the presence of radiation from the sun affected the ozone layer, basically recombining it with the chlorofluorocarbons to reduce it. And not good because we started seeing ultraviolet radiation coming through over larger areas than would normally be expected. So, even people in ivory towers can get skin cancer from UV radiation. So let's do something about that. So what we did was we found the CFCs that were kind of at the top of the list, the more energetic ones, and we said, let's ban all those. Well, what about the rest of them in the list? Ignore those for the time being. So today we're still doing hydrofluorocarbons and hydrofluoroolefins, hydrofluoroolefins. But we recently started to ban some of those because it turns out, remember the pandemic when everybody wanted everything shipped to their house? Turns out the adhesive they used in a popular brand of packing tape, the adhesive was producing CFCs, this outgassing. And they noticed that the ozone hole over the Antarctic started to get larger with everybody wanting everything shipped to their home. So they, knocked on 3M's door and said, could you guys stop using that adhesive? So they did. And has anyone ever heard of forever chemicals? These are PFAS or PFAS. There's two major groups, PFOAs and PFOSs. Those are in plastics. Those are very long chain. And look, they still have the F letter in there, which means fluorides, fluorine element atoms in the compounds. And that causes the chain to be even longer and longer and more durable. Turns out those can actually get into the human body from you doing things with plastics, and they stay there. Now, this is not the microplastics. This is the chemical structure of the plastics, not like the size of the chips and stuff. And now they're banning PFASs, and one of the latest ones is 3M has decided, okay, we're going to just not do PFAS at all. And by 2025, we'll neither be shipping them or manufacturing them. Why not immediately? Well, it's difficult to get off the addiction to certain plastics and to make new formulations. So at least for now, some are still in the system, but by 2025, 3M will stop. Now, 3M is a worldwide large manufacturer, but that doesn't say that every plastics manufacturer will stop. Now, we know kind of what issues with temperature rise and sea level rise and things like that, and we're not going to get off on that tangent, but we've transitioned from coal to fuel oil to natural gas to gasoline, jet fuel. We've now got companies like Florida Power and Light going, we did the whole transition from coal to fuel oil to natural gas, and we're finding that those solar panels out in the Everglades are really doing a bang up job, and we put batteries behind them. So we can probably not run the natural gas fired power plants as often. So it's a financial incentive. There's no government edict. There's no, thou shalt do it by this date. It's just money's better. And if you have your own power from the sun, somebody over in another country can't say, we're raising the price of what you're burning. The sun is the sun. It's not going to get more expensive. Now, fission-based nuclear power we've had for a long time, and the plants that do operate and are still operating have done a marvelous job with safety, but in risk assessment, if something can go wrong, even if it's a very small probability, if the side effect is very disastrous, like, oh, that area for the next, 1,000 years is dead, or we killed a small number of people, that's not good. So you can think of Chernobyl and Fukushima as, yeah, they don't happen all the time, which is good, but when they do happen, things can go really bad. But we also have processing. When you want to go make those nuclear fuel rods, there's debris left. There's basically, you're washing chemicals around that are now radioactive. You're washing substances around, cleaning things, and the garb that you wear as an engineer is disposable. So it's radioactive. How do you dispose of it? You put it all in giant concrete cylinders and seal them up and put them in a cave for the next 1,000 years. That'll work, yeah. So even if we stop producing power in power plants and went with renewables, we still have aircraft carriers and submarines that are fission powered. And we still have to process fuel for them to restock them. I heard that the latest aircraft carrier, its fuel should be good for 50 years. Now, the fuel itself isn't good for 50 years. When they commission the aircraft carrier, they put on board enough fuel rods so that the fuel supply that's on the ship is good for 50 years. And when they take the rods out, they'll just sort of sit them over in the corner on the ship. So at the end of 50 years, when they decommission the ship, is when they'll worry about what to do with all the spent fuel rods. Hopefully by then we'll figure out what to do with it. But it's nice to be able to have a fuel that you don't have to worry about on a regular basis, but the side effects are still there. And here's a few more that I didn't get into details on that you probably have heard of, like burn pits as a means of destroying toxic waste up until the ash and the smoke start blowing downwind to people. Remember dial soap? So good we use it on little babies, and it had hexachlorophene in it. And we found out that's probably not good. But guess what? Acne soaps, like the cleansers you use when you have acne as a teenager. There's 2 brands of acne soaps that still have hexachlorophene in them. And only in the last couple of years, there was a mouthwash that your dentist would recommend after you had some dental surgery that had hexachlorophene in it. And they said, when people gargle, not all of it gets out. Some of it accidentally gets swallowed, and that's probably not good. So they changed the chemical formula away from hexachlorophene to another chlorine. Okay. How about lead in paint? Neurologically affecting military maintenance personnel. Painting that lead ship, get that swabby down there, paint that lead on the ship, which makes the lead more durable and makes it where it doesn't grow algae on the outside hull of the ship, which slows the ship down. But as far as I know, they're still painting lead on ships, but it's been banned in consumer products. So if you go to Home Depot or Lowe's or Sherwin-Williams and you buy paint for your house, inside or out, it's absolutely not going to have lead in it because that was banned by federal policy. But you go into the military and you get, I got to paint the ship, or I got to paint the fuel tanks if you're in the Air Force or the Army. There's still lead in those because don't want them rusting. There was a time when we actually looked into military aircraft being nuclear powered. We even looked into tanks, like military tanks on the ground being nuclear powered, because nuclear is so cool. It costs a lot of money, but it'll last a long time. It's not you got to go fill up a fuel tank. It's you put the fuel rods in and you're good for about 3 years. But I think Casimir module electric power is probably where we're going to be in the future. How about rocket propulsion? We actually, back in the 1950s into early 60s, looked at using rocket propulsion that was essentially blowing hydrogen through a radioactive core, and that increased the propulsive force and made the rocket last longer because the fuel didn't burn up so quickly, and also more power. So great. And they were testing them on the ground with the nozzle of the exhaust pointing upward. And they noticed that radioactive spikes were happening in cities nearby where the rocket engines were tested. And they said, that's probably not a good idea. Let's stop that. So, but people that are newer than that were born later, are going, hey, why don't we try nuclear propulsion rockets? That can't go wrong. Hey, here's an old design. Let's use modern electronics, but the same concepts. So yeah, not good to resurrect some things. But I'm just driving home that historically we've had our downsides, and for us to come up with yet another boneheaded maneuver doesn't look good for us. But someday we could do something really, really bad and end our days, so to speak. But not yet, so let's keep trying. But I'm not gonna bash a dead horse, so to speak here. I could fall back on one or two phrases, forgive them for they know what, not what they do. But they seem to want the profit. And even when they find out that's not a good thing to be doing, oh, but the profit is so good. They have to be pushed to do it by, it's bad for all of us, not just for you. And then fall back on another movie phrase, which is best laid plans of mice and men. What do men have to do with it? Hitchhiker's Guide? I mean, just me. So here's our contemporary stumbling. So we know there's these asteroids and comets out there, and some of them might have our name on it, so to speak, might have the name Earth on the side of them. So we'd like to know how we deal with them. And we thought, let's blow them up, because that always works in the movies. So they said, well, we don't want to really blow it up. We just want to find out if we take something heavy and fire it off at it very fast, and it becomes an impactor, like impacts the asteroid, that force, and it's just the mathematics and physics of, F equals ma, how much force we're applying to it. It doesn't have to be an explosion. It doesn't have to be a nuke. It can just be like something heavy, flying fast, hitting it. So we said, what could go wrong? Let's do that. But we may not have considered some things. As it turns out, most of those fast-moving, smaller things that are flying around the solar system, they're not solid. They're not like, dense rock or metal or rocky metal. They're rubble piles. And a rubble pile is just, if you've got some dust, the dust is going to start to coalesce or cling together due to static electricity. And then you collect a little more dust and a little more dust, and now you start to collect in maybe some sand, gravel, and now you're building up gravitational force, and the gravity starts to build up. And it's kind of like a wrapper on top of a wrapper on top of a wrapper. And it gets bigger and bigger. And now you have this thing that might be, a lot of meters to miles across, and you look at it and you go, well, from Earth, that looks solid. Because, we can't see fine detail that far away, millions of miles away. But, our radar images and our pictures from Hubble and the James Webb Space Telescope, they all look like this thing's solid. So let's have an impactor go hit it and see if it changes its orbit. So we picked a small one that was orbiting a big one, millions of miles away from the Earth, thinking that was going to be safe. And as we already committed to impacting it, the camera that we're shooting as we arrived took this picture and went, guys, I don't think it's solid. The actual phrase they used was, clearly, it looks like a collection of rocks. And if you were to mix up varying size of boulders, rocks, pebbles with silt and dust and salts and ice, that's the kind of thing you'd get. It's not held together very strongly. So you go in there and you throw a lot of force with an impactor into it. This thing is going to splash, and it's going to throw light stuff a long distance and heavier stuff a little further distance, and the heaviest stuff will all fall back. So that's what happened is we threw an impactor at this thing, splash, not explosion, splash. It didn't vaporize it, splash. A lot of the stuff came out of it. And some of the stuff that left it never coming back anytime soon because it's very lightweight and it got accelerated away. The slightly heavier stuff, it might fall back to it, or it might go into orbit around the bigger thing and make new things around the bigger thing, or it could fall onto the bigger thing from gravity. But, there are things in our solar system that are bigger and are harder. And we don't actually have the nuclear capacity to blow those things up. We're just picking the small stuff. And there are things in our solar system that are either gaseous or balls of water covered in ice. And you could try and blow those up, but they'll just go splash and reassemble. So we're going to be focusing on those moderate-sized rubble piles. What's the old phrase? If you can't blow it up, nuke it. Well, even though we're no longer detonating them in space, on the ground, or below the ground, we're improving the technology of them, or so Los Alamos National Labs exists for that purpose. Anything that gets in our way, if it's really big and we want to get rid of it with a lot of force, nuke it. So anything big and difficult, that's our more than a, what's the old phrase? If all you've got's a hammer, everything looks like a nail. This is even worse than that. If it looks big, we don't evaluate whether it's a nail or not. Just nuke it. Works in the movies. Did you know that one time we thought about building navigable canals on Earth using nukes instead of like building the Panama Canal with lots of people and lots of shovels hauling away lots of dirt? What if we just set off a series of nukes along the path of the canal? That would like blow it open, and then we just let the water flow through, and that'll scrape it all out for us. And we wouldn't have to haul away a lot of the dirt because the nuke will just vaporize it. And then you have to think about fallout, dust. What you blew up is going to be radioactive. So the water flowing through it is going to pick up the silt, and you're now going to have radioactive silt outflows at both ends of your canal. And so this was called Operation Plowshare. You can look it up. There's a link at the end. And we decided that's probably not a good idea. But every time we go to build another canal, another major canal like the one they want to build across Mexico, it's, have we thought about nuking this? Yeah, and not a good idea. Let's find a different approach. But it works in the movies. So here's a picture that was taken by one of the probes that came along with the NASA mission called DART, the Double Asteroid Redirection Test. This is where you had a moderate-sized asteroid with a smaller asteroid orbiting it, and the impactor hit the smaller one, and we hit it at the right direction to try and slow it down. We sort of retarded speed to see how that would change not only the smaller asteroid shape, but also its orbit. And we can do the mathematical calculations and decide if we made it bigger or we used a nuke, would it slow down something even bigger sufficiently where it wouldn't hit the Earth anymore? And what we found out was it's a rubble pile, and we kind of blew it up. Now, the spike that you see going up towards the left, think of a comet. If I have a comet and has a debris trail of fine dust, and the sunlight hits the debris trail, I see the tail. So this little asteroid going around the bigger asteroid actually formed a tail that was visible in camera images. So that's kind of that's the fine stuff it just splashed out everywhere. And based upon the solar wind, you could have long tails and short tails. But also think about it this way. All that dust that left is not coming back. So all the dust that was actually holding things together at a very fine grain level, it's no longer there to hold things together. So the smaller, non-dust, pebblish kinds of things no longer have the silt to seal it over to make it hold tighter. It's going to be even looser rubble pile now. Well, it turns out they don't have actual examinations on all the particles, but they've done some simulations based upon what they saw fly off and radar images that they've taken since then. And it turns out that there are no big stuff headed towards Earth. Good. There are some small to moderate sized stuff headed for Mars. Okay, so luckily the big stuff's not coming to Earth, and what does arrive, they expect to burn up. This is where the meteor shower comes in. Are we going to have one? Or are we not going to have one? I don't know. How dark is it out there? Luckily, we currently have no colonies on Mars, no habitats, no people on Mars. If we did, then they actually predicted that some chunks would actually hit the ground on Mars. So, the simulations don't take everything into account. The radar imaging may not have looked in all directions sufficiently to take everything into account. So we think we got it all, so to speak. So this artificial meteor shower stuff, where is it? When is it going to hit us? How often is it going to hit us? The impact actually took place in year 2022, so we're 2 years after that. It was 11 million kilometers or 7 million miles from Earth, way out there. Don't worry about it, it's way out there. About 1,000 tons, roughly, of material was ejected off the asteroid surface. The solar wind caught all the light debris, and that's where you get the tail from. We've done imaging with Hubble and James Webb and Earth-based telescopes, as well as deep space radar that's Earth-based. And we're tracking hundreds of pieces and clouds of debris of varying sizes from this one impactor. And remember, no explosives, no nukes, just something heavy, very fast, smacking into a rubble pile. Now, amazingly, the small stuff is expected to burn up. Mars has a thinner atmosphere, so maybe some stuff will hit there. There are larger items, but they're not currently headed towards Earth or Mars. The arrival date for the first debris at Earth is 2029 to 2052. Why so long? Well, because, the explosive force made the light stuff come out quicker, faster, and the heavier stuff followed it. So it's not just one event, it's a stretch of them, 2029 to 2052. And that's the first go round. Every year, we're going to plow back through the same stuff. So it could happen again. Things move in space. The solar wind moves things in space. So what misses us this cycle could hit us the next cycle. So some of that bigger stuff that we were tracking going elsewhere, we could hit another time around. The conclusion is, hey guys, don't ever do that again. Or if you're going to do that again, make sure it's not a rubble pile well in advance of deciding to launch your impactor. Don't wait until you've got the impactor homing in on it going, wait a minute, that's a rubble pile. Evaluate that before you even launch. So here's some of the details of it. The two asteroids were called Didymos. This is the larger asteroid, and the smaller one, which is actually considered a moon of the larger asteroid, is called Dimorphos. And like I said, 11 million kilometers, 7 million miles away. These items are actually part of something called the Apollo group of Earth orbiting asteroids. There's a lot of them. We'll get to that on the next slide. The orbital period of Dimorphos was 11.9 hours. So how long it took for the smaller guy to go around the bigger guy was about 11.9 hours. The impactor hit the smaller guy at about 6.6 kilometers per second, or 4.1 miles per second. We were deliberately accelerating it as fast as we could get it to go because the F equals ma says bigger hit. No explosion necessary, no explosives necessary, no nukes necessary. Just hit it as hard as you can. The idea being, if this works, then maybe someday in the future we could save Earth by a larger impactor or an explosive or even a nuke. So dust, silt, all kinds of stuff were coming off of this thing for a while. We now have an even looser rubble pile than before. It actually made a crater on the asteroid and reshaped the rubble pile. So instead of being closer to being round, it's more elongated. We don't quite know precisely what was left because it's still coalescing. The bigger stuff has already coalesced back onto the smaller and the larger one. The lighter dust is still kind of finding its way back either through static electricity or through gravity. The European Space Agency is going to send a probe. They're going to launch it this year in, I think, October. It'll arrive at Dimorphos in 2026, but it's going to take pictures of what it looks like now and also the orbits, because this large an impact not only altered the shape and the orbit of the little asteroid, it actually altered the trajectory of the bigger asteroid. So we have to go back and reevaluate that by close-up observation. Some other things that we learned along the way. Objects in space may not only be a rubble pile, but the rubble pile may have buried in it large boulders. So if you see something that's 5 miles across, there may be a couple of big chunks that are each a mile across inside what looks like a solid object, but it actually just is loosely held together. And they can be shaped like all sorts of things. And the reason why something might be shaped like a dumbbell, like, two large lobes with a joining, is the lighter stuff is in the middle and wrapped around the outside of two bigger pieces. If they get big enough, then gravity will, through hydrostatic equilibrium, sort of smush it down to being more spherical. We also learned that in space, things can orbit things. So if you have something small, it can orbit something larger, even though both the small and the large aren't that big. And we also learned from a different probe that orbited asteroids that if you have an asteroid that's not quite spherical and maybe a rubble pile, the gravitational field of that body is not simple. You may go through Lagrange's curves in order to orbit that thing. You may start out on an orbit and never get back to where you were because the object is rotating and the gravitational field is changing. So it's not always easy to predict orbital arrival at these things. And if something's rotating slowly, you can probably land on it to, put a thruster there or something, or you can, send an impactor in to blow it up because you know exactly where it's going to land. But if you encounter an object that you want to get rid of and it's rotating fast enough, you may not be able to land on it. You may not be able to have a perfect impact site to do the damage you expect. So there's some variables you have to think about there that we didn't think about before. Now we are. The surface of something may be different on different parts of it. We saw on an asteroid that a different probe went around that there was a large number of areas that were very white and reflective. Salts mixed with ice. So the sunlight reflecting off of that causes a force to be applied to the asteroid. radiation reflection pressure is a thing. So as the object is rotating and has some salty reflective spots, every time that presents itself to sunlight, it gets a little push in that direction. So orbits can change seasonally because the ice and water areas can go from solid to liquid as the thing rotates seasonally. So you have to take that into a calculation as where's it going to wind up? So I mentioned the Apollo asteroids having nothing to do with the Apollo space program. It has more to do with, mythology and Greek gods and things like that. It's named after a very large asteroid that was detected in 1862 called Apollo. They named it Apollo. Back then we used to have mythological names. Now it's kind of a hard stretch once you start finding thousands of these things to give them anything more than a number, like the year it was found and a letter and to say kind of what month and then which number did you find it in the month. So the Apollos are part of a number of asteroid fields. There are two of them that we're concerned about. One is called the Apollos. The other one's called the Etens. The acronym form is APO and ATE. These are what is known as Earth-crossing asteroids. So it's not like, rocks like you'd see in a space movie where they're all real close together and they're all roughly the same size. This goes from silts to pebbles to gravel to rock to boulders, all different size stuff, having a stable pattern orbiting the sun. But the orbit is slightly shifted. It's not perfectly circular. So its orbit is elongated in the path of Earth. So as Earth orbits the sun, there's a certain number of days every year that we're in the path of the Apollos or the Etens. Within that collection, there's about 2,000 of them that have been identified as potentially Earth hazardous objects or PHOs. The largest in the Apollo group is something called 1866 Sisyphus, and it's about 8.5 kilometers or 5.3 miles across. As a point of perspective, if you remember that meteor that came down in Russia, that was only 18 meters or 59 feet across, and it was from the Apollo group. So yeah, it makes sense for us to figure out how we're going to deal with it if we find one that's a problem. But, we've also learned that blowing stuff up is not the way to go. So if we can't blow it up, what do we do? Well, we have to be more subtle. Maybe what we should do is have full-time radar to examine things in space, and sole purpose is to look for the potentially hazardous things. But we can't find all of those because some of them come in from the direction of the sun. That's when you see things like, hey, we just found another asteroid. Really? When's it going to come by? Oh, it already came by. We found it as it was departing. It actually came lower than geostationary orbiting satellites, but we couldn't see it because it was coming in out of the sun. So we need to have radar at another point in space to look back so it's not staring into the sun. There's a trans-Neptunian object, nice long number and name there, that's about 39 astronomical units out in space. That would be a good place to put it because it has a slow orbit, 2 hours. So you could be scanning space like a radar dome. So if you found something that was hazardous, what would you do? You could take an ion thruster and land it on it with a big old fuel tank, and every time it was facing in the right direction, you could turn on the ion thruster and push a little bit with it. Remember, if it's really spinning fast, you're not going to land on it. And it's got a fixed fuel tank. You're not going to go and refuel the fuel tank. So whatever you land with is good for about 5 years. You could spray paint it. You could spray it with ices or salts onto the surface of it to make it reflective and therefore let the sun do the pushing on it, hoping that it's going to be spinning in the right direction so that when it gets pushed in the right direction. You could have an orbiting probe that is a gravity assister. So just having a very large probe on the correct side of it to kind of tug on it gravitationally, could do that. Or you could be ablating it. You could have a gigawatt laser orbiting it and just blowing debris off the surface of it. Hopefully it's just fine particles, no big rocks. Or this one's interesting, maybe even profitable. You could reduce the mass of it. Reducing the mass of it will change its trajectory. Now, how would you do this? Well, you could either land on the surface and haul away tonnage, which is like a business, or you could use small impactors that will blow off a small amount of rocks, and you could suck those in and then, have a multiple ship fleet that just slowly reduces the size of it and maybe deposits it elsewhere, drops it into orbit around, I don't know, Venus, assuming that there's no life there, or Jupiter or Saturn, but maybe make some mining money in the process. So in conclusion, just because you have military weapons of mass destruction, for when diplomacy fails or arrogance dominates over empathic intelligence, doesn't mean you should go around looking for, hey, we can try it out by blowing up asteroids or comets. Something in space that may appear solid from here on Earth, that's no assurance that it's solid when you actually get out there. The DART mission taught us that rubble piles do exist, and that absent other forces, even static electricity is enough to start making the snowball grow. And eventually you're going to get snowballs that can be miles across, but are still just rubble piles. Disrupting them with explosions after it took millions of years to aggregate all that stuff, this stuff can go off in all directions, maybe even back to Earth. And we already know that from what we've done, things are going to be coming back, certainly to Mars and hitting the surface, but also interacting with the Earth's atmosphere. Not, threatening of life, but maybe we'll get a meteor shower. So alternatively, what we should be doing is thinking about the slow, long game, a gravity attractor, ion drive, or put a solar sail on it, or maybe haul away stuff, create a new business. And links. So how many people saw basically NASA ignore the man behind the curtain press release that came out today saying there won't be a meteor shower? And then a day before they were saying there's going to be a meteor shower as a result of what DART did. And then other press items that came out saying DART was really wonderful. It did exactly what we wanted it to do, except the whole part about rubble piles. So whenever you think you got a good bead on things, you might want to get a second opinion.
At least.
Yeah. Comment?
Something entered the atmosphere over North Carolina yesterday, and as of yesterday, when I read the article, they weren't sure if it was a meteor or man-made debris.
Yeah. Well, if it completely burns up, they won't know.
They thought pieces might have landed.
Yeah. If it's landed, then you can probably figure out whether it was man-made or not.
Yeah.
But also, strangely enough, if you take high-quality pictures of it breaking up, you can look at the colors in the picture and decide, is it stony or is it metallic? And if it's metallic, based upon the colors, what kinds of metals were involved? And
one of the people interviewed did mention several colors and color changes as it was coming.
Yes.
Yeah.
Well, there are stony metal meteors that do exist, and they can have other metals in them. The one that is always a dead giveaway for it came from space is iridium. There's so little iridium on the Earth. Earth itself is iridium poor that that line of sediment that contains iridium must have come from a big asteroid hitting the Earth. And you don't find a lot of that up and down. But if you see something burn up and you do the chemical signature on it and you find it has iridium in it, it's a pretty good guess it came from out there. Any other comments or questions about the presentation? Okay, I will stop recording.